So, good night. Let's get started. So, for the first, I will explain the Rabbit-Miller algorithm to detect and test if a number is prime or not. So, basically, what I did was two functions, where I first, to explain first, I developed a function where it determines if a number is prime or not before calling the Rabbit-Miller, because if I enter a number which is easy to determine, then I can not call the function of Rabbit-Miller. So this is a fast check, in other words. So I check first that the number I enter that if the number is minus than 2, it returns false because I can't accept zeros and ones and negative numbers. So then I created a list of known primes all the way from 2 to 1,000, the range of primes. So then I checked if the number is in the list of low primes, then I return true. Then it's prime number. Then I see if any of the low prime numbers can be divided by none, and if it's even, it means that it's not prime because it's composite. So it returns false. If else fails, all of these fail, then I call the Rabbit-Miller to determine if the number is prime. So now to explain the Rabbit-Miller function. So basically here it follows the principles and the theory behind the Rabbit-Miller function and test function. So basically I have a variable s which subtracts by 1 the number which I'm going to test, and then I establish a counter. Then I keep doing halves by 2 to determine if it's pair. If it's pair, I will be doing a forward division and be counting by 1, tease the counter to develop how many times I have to use to determine the comparison in the test. So basically then I do a loop of 20 times because the requirements under the document of the professor said that it needed to be 20 times. So basically here I repeat this by generating a random number from the range of 2 to the number minus 1. Then I raise a power using the power function of a, s, and none, raising the number generator using s and by the none. And this test does not apply if v is 1. So then I initialize the 0, and while this is not number minus 1, then I check if it's t minus 1, because in the theory and the principle, the checkings of the Rabbit-Miller, if it's equal to t minus 1, then it returns false. It's not prime, it's composite. Then if not, I will do the summation of I and keep doing the formula, which is raising to the power of 2, and then calculating the modulus unknown. And I repeat this 20 times to try to falsify the Primality 20 times. So then for the prime selection function, I use the library of SymPy. So there's a built-in function called next prime, which I pass the number which I'm going to search for the prime larger than this, and then returns that prime number. And then I check if it's prime. If it's true, using the Rabbit Primality test function, then I return the number. If not, then it doesn't exist. So next, for the modular explanation, I developed the right to left and left to right required by the document. So basically what we are doing here is I'm initializing the R in 1 and basically doing a repetition of calculations while it's 1, and does the break here because I'm checking here, and if it's on pair, I will do the calculation with the R established by the Modular Exponentiation formula. and then I will keep dividing by 2. So it will shift all of the bits from right to left and keep doing that calculation with the remainder and keep shifting it to right, from right to left, sorry. Then if it's 0, it does a break. It would terminate the function. If not, then it will calculate the base and keep doing this and this and this and return then R, because R is the modular exponentiation function. So for the left to right, I establish a second function I'll explain later. Sorry. So basically, I'm doing the same, initializing the R by 1, but I'm using a built-in function using reverse. So I will traverse this list, because this function is a list, returns a list of the number I will pass here, and then it will calculate the same function but in reverse mode and check if it's the bit that is 1. Then it will do the calculation, but instead of R, with the base of A, and then it will return R. So for the complete bits function, this GCD and multiplicative there's no need to explain, because I already developed it in the previous project of AES. So basically, in complete bits, it's a transformation of the number in its binary representation. So basically, what I'm doing here is a modulus 2, which is 1s and 0s, and I will append it to a list I created here. And then I will keep having the n by 2, and by 2 by 2 I will be appending it to a list, and I will traverse it in reverse for the left to right, and this will keep shifting from left to right, and this right to left. So for the key generation in RSA, basically I have P and Q, which are two prime 64-bit prime numbers, and then I check if both are prime or if it's equal. If they're equal, both, or if they're not prime, it will deliver an error. Then all here is the principles of the RSA scheme, which establish that n must be multiplied by the P and Q prime numbers, and the totient of the calculation of the totient, it's -1 multiplied by Q minus 1. Then I choose an integer such that E and Phi are co-prime, which is a generator between 1 and 5. Then I use the Euclidean to verify that E and R prime here, the GCD, and while this is not 1, I will keep doing that same calculation until it's not 1, and do then if the generate private key, which is the multiplicative inverse between E and 5, and then I return the private, which is the public and the private key. For the encryption, it's very straightforward, because I use for the private key using the key and then I convert each letter in the plaintext to numbers based on the characters using the function established in the RSA scheme, which is using the function of the RSA scheme, which is the ORD built-in function of Python 3, which uses the Unicode value of the char and raises it to the key and using a modulus of n for every char in the plaintext, and then I return the cipher. And then for the decryption, also it's just the same, but instead of using ORD, I use the char to represent the string and the plaintext. And then for every char in the ciphertext, and then I return the encrypted message. So for the modular exponentiation and test, I call the function and use a base 2 of exponent 11 and modulus 19. The modulus 19, and it's supposed to give the same result between the two, because I'm using the same base and exponent modulus. So for the middle-variant prime selection, basically I'm calling the prime selection function, which is the 32, 64, 128, and 256 in the prime, which are this. I calculated them individually, so it will determine the prime selection, which is a prime number larger than this ones I pass on the as parameters. So then for the RSA, I stored the P in the input value and the Q in another input value, which is different from P. Then I put the public and private keys using the key generation I explained earlier. Then the message to decrypt as an input and stored in a variable, and then I encrypt the message, which is encrypted here, and then I decrypt it. So basically, these are the results. Sorry. So these are the same, like I said, and these are the results of the prime selection functions. So for the RSA, I use 71 as P and then Q as 19, and I encrypted the message hello. This is an encrypted message, which is in Unicode value form, because it needs to be in this value to be calculated then into the decrypted message, and the decrypted message is done correctly. So thank you very much.